Welcome to Chapter 16 about virtualization. Let's dive in. So, in the 1960s, the computing community was frustrated by the problem of sharing resources like memory, disk, input output channels, user input devices on one physical machine, and several independent applications. And this inability to share resources meant that only one application could be run at a time. So computers at that time cost millions of dollars, and back then, I mean that's a lot of money now, but back then that was a significant amount of money. And most applications only used a fraction, maybe 10% of the available resources in the machine itself. So this situation had a significant effect on computing costs, very literally. Virtual machines and later containers emerged to help deal with this sharing. And the goal of these virtual machines and the containers is to isolate one application from another while still sharing resources. Isolation allows for developers to write applications as if they're the only ones using that computer, while sharing those resources allows for multiple applications to run on the computer at the same time. So why is this a topic of interest and concern to architects? Well, as an architect, you may be inclined or required to use some form of virtualization to deploy the software that you created. And so this is just an interesting quote from the beginning of the chapter. Virtual means never knowing where your next bite is coming from. It's taking kind of a fun play on words like a bite of food versus a bite of memory or processing power, and trying to figure out where those resources are coming from very literally in your software system. So for economic reasons, many organizations have adopted some form of shared resources, and these can really lower the cost of deploying a system, whether it's a shared system of servers or in many cases now virtual machines. That's a great way to reduce costs. There are 4 resources that we typically care about when we're sharing. First is your central processor unit, your CPU. Modern computers have multiple CPUs, and each CPU can have multiple processing cores. And they can also have one or more graphics processing units. Those are your GPUs. They could have special purpose processors like tensor processing units, TPUs, lots of different things. So it's important to be thinking about that central processor unit as we think about sharing. Next up is memory. A physical computer has a fixed amount of physical memory, and that memory is necessary for processing events and information. Disk storage. Disks provide that persistent storage that sticks around for instructions and for data, and that persists it keeps it there across reboots, shutdowns, events like that for the computer itself. A physical computer typically has one or more attached disk, and each of those attached disks would have a fixed amount of storage capacity. And disk storage could refer to either a rotating magnetic or optical hard disk device or a solid state disk drive device. The difference of those, the rotating magnetic, I remember, and these are not quite as common now. It's very nice to have the solid state, but I remember when I got my first really big external hard drive. It was 1 terabyte. That was huge. It was a big investment for me. But it was, we didn't have solid state at the time. It wasn't a thing. And I remember getting a bunch of things backed up on it, clearing off my computer, and then somebody tripped over the cord that had attached it to the wall, and while it was spinning, it took a fall. And the problem with that is if something is spinning while being jostled around, you can imagine that that can scratch or damage that spinning disk, which then meant I could no longer access any of the data that I had just moved on to that. So solid state is very nice, especially if you are moving around or things get jostled. So solid state doesn't have any disks or moving parts. As the name implies, it's a solid state. Regardless, you need some form of disk storage. And then we also have the network connection. So even today, back then maybe it was less common to have a network because maybe you had just one big machine. But today, non-trivial physical computers usually have one or more network connections. Think about your phone. I mean, it's a small device, but it is constantly on the network. And now it's quite common to have Wi-Fi access everywhere, but also cell signals are pretty good in many places, and you can get data wherever you are. So even though you're not wired in, you can still get that network connection. So some form of network connection is necessary for shared resources. So now that we've gone through some of those resources that we want to share, we need to think about how to go about sharing them and how to do this in a isolated way so that different applications are unaware of each other's existence. So a processor sharing is achieved through a thread scheduling mechanism. So you have your threads as things are happening. So the scheduler selects and assigns an execution thread to an available processor, and then that thread maintains control until the processor is rescheduled. So until another thread is scheduled to it. No application thread can gain control of a processor without going through the scheduler, and rescheduling occurs when the thread gives up control to the processor, or when a fixed time interval expires, or when an interrupt occurs. So there's a few different ways that a processor can get control back, but generally it's the thread that will give up control. Historically, as applications grew, all the code and data wouldn't fit into physical memory, and so virtual memory technology was developed to deal with that challenge. Memory management hardware partitions the processor's address space into pages and then swaps pages between that physical memory and secondary storage as needed. And the pages that are in physical memory can be accessed immediately, and the other pages are stored in a secondary memory until they need it. So kind of like having a stack of papers, you've got one paper in front of you at all times, and you can swap it out for a different paper in the pile, but you can only have that one paper in front of you at a time. So the hardware supports the isolation of one address space from another. Disk sharing and isolation are achieved through several different mechanisms. First, there's the physical disks that can be accessed only through a disk controller that ensures the data streams to and from each thread that we talked about, and that they're delivered in sequence, in order. And the operating system could tag executing threads and disk content, like the files and the directories, with information like user ID and user group. It could restrict visibility or access by comparing tags to the thread requesting access and the disk content. So network isolation is achieved through the identification of messages, and every virtual machine, VM is what you'll see, the abbreviation. Every virtual machine or container has an Internet Protocol IP address, which is then used to identify messages to or from that virtual machine or container. Let's talk about virtual machines. Now that we've seen how resources use one application and can be isolated from the resource usage from another application, we can look at and combine these different mechanisms that we just briefly went through. Virtual machines allow the execution of multiple simulated being virtual, multiple virtual computers in a single physical computer. So virtual machines, we'll say it again, virtual machines allow the execution, the running of multiple virtual machines on a single physical computer. To help show what I mean, here's an illustration from the book. So you have the physical computer, which in this picture is called the host computer. It's the light gray that kind of encompasses the whole thing. That's your physical computer, the one that you could sit down in front of you and dust off and plug into the wall. And then your virtual machines, your VMs, are called the guest computers. There's this other bit called a hypervisor. And the hypervisor, in this example, a bare metal hypervisor, this is type 1, it runs directly on the physical computer hardware. And because it's running on that hardware, it's called a bare metal hypervisor. Because if you were to open up your computer, generally you would see bare metal inside. So the virtual machines that this hypervisor hosts that the physical machine hosts, they implement the applications and services. And then the bare metal hypervisor, which typically would run in a data center or a cloud, which we'll talk about in chapter 17, those are kind of helping to control things. It's like they're like the operating system for the virtual machines. Okay. Now we have a second type of hypervisor called a hosted hypervisor. This is type 2. And in this case, the hypervisor runs as a service on top of the host or on top of the host operating system. And then it itself hosts one or more virtual machines. So hosted hypervisors are typically used on a desktop or laptop computer. If you did a lab assignment with me, then you set up a virtual machine like this with a hosted hypervisor using something like VirtualBox. These type of hosted hypervisors allow developers to run and test applications that are maybe incompatible with their computer's host operating system, like running an Linux application on a Windows computer or a Windows application on an Apple computer. They can also replicate a production environment on a development computer, even if the operating system is the same. And that approach allows for development and production environments to match each other, which is very useful, as you can imagine. A hypervisor requires that its guest virtual machines use the same instruction set as the underlying physical CPU. The hypervisor doesn't do any translations, and it doesn't simulate instruction execution. So, for example, if you have a virtual machine for a mobile or an embedded device that has an ARM processor, you can't run that virtual machine on a hypervisor with an x86 processor. Another technology related to hypervisors that supports cross-processor execution is called an emulator. And you may have heard of emulators before. I've got a picture of a Raspberry Pi that's running an emulator so that it can play old school Nintendo games. So an emulator reads binary code for the target or the guest processor, and then it simulates the execution of those guest instructions on the host processor. The emulator often simulates guest input-output hardware devices like Nintendo controllers. And emulators like the one on this Raspberry Pi can be used to run classic console games, which is pretty fun. So you don't have to have the old buggy software where you have to blow on the cartridge, which is very fun and very cool. You can instead save yourself a little bit of extra time and frustration and run an emulator, and then have access to games that you don't need the hardware for. All right, so hypervisors, what are they? Code that communicates outside the virtual machine by accessing virtual disk or network interface is intercepted by the hypervisor and then executed by the hypervisor on behalf of the virtual machine. So it manages the code running on each virtual machine. By intercepting the communication, this allows the hypervisor to tag the external requests so that the response to these requests can be routed to the correct virtual machine. And the response to an external request to an input-output device or a network is then an asynchronous interrupt. And the hypervisor initially handles the interrupt, and since multiple virtual machines are operating on a single physical host machine, and each virtual machine may have input-output requests outstanding, the hypervisor needs to have a method for forwarding the interrupt to the correct virtual machine. So it's also important to recognize that virtual machines need to be managed. So hypervisors manage the actual virtual machines. For an example, virtual machines need to be created and destroyed, among other things that need to happen. Managing those virtual machines, again, is a function of the hypervisor. The hypervisor doesn't decide on its own to create or destroy a virtual machine, but it acts on instructions from a user or more often from a cloud infrastructure, which, again, we'll get to in chapter 17. So creating a virtual machine involves loading an image, and this is going to be discussed in the next section, and we also did this as part of our lab when we set up virtual machines. In addition to creating and destroying the VMs for that management, the hypervisor does monitoring as well. Health checks and resource usage are part of that monitoring. The hypervisor is located inside the defensive security perimeter of the VMs as a defense against attacks. And the hypervisor is responsible for ensuring that a virtual machine doesn't exceed its resource utilization limits. We care about how much it's using the resources. Each virtual machine has a limit on the CPU utilization, the memory, and disk and network input-output bandwidth. Before starting a virtual machine, the hypervisor first ensures that there is enough physical resources available to satisfy the needs for that virtual machine, and then the hypervisor enforces those limits while it's running. Okay? So hypervisors are all about managing the code running the virtual machine and managing the virtual machine itself. What are the major implications of virtual machines for you as a software architect? First, we care about performance. We need to be concerned about that because virtualization does incur a performance cost. There's the type 1 hypervisors, and they only have maybe a modest performance penalty, but type 2 hypervisors have a much larger overhead with their resource usage. We also care about a separation of concerns. We want to be able to pull out what is being thought about and concerned about with the software and what's being run. So virtualization allows an architect, you guys, to treat the runtime resources as commodities. And by treating it that way, we can defer the provisioning and the deployment decisions to another person or another organization. So we can separate out those concerns so that we can delegate as necessary. Virtual machine images. We call the contents of the disk storage that we boot a virtual machine from a virtual machine image. The image contains bits. Bits are bits of information that represent the instructions and the data that make up the software that we're going to run. So, for example, the operating system and the services that the virtual machine is running. The bits are organized into files and directories according to the file system used by your operating system, and the image also contains the boot load program, which is stored in its whatever predetermined location. Okay, so the image contains all of that information that we need to boot up that operating system. So let's look at creating new virtual machine images. There are 3 different approaches that you can use to create a new virtual machine image. The first one is to make a snapshot copy of a machine that's already running the software that you want. So making a snapshot that copies the bits from that machine into memory. So that's a nice, easy way to do it, is find a machine that is running what you want and get a snapshot of it and build your image from that. You can also start from an existing image, which for our lab, most of you probably did that. You went and used VirtualBox and then looked at a library of images, downloaded the image that you needed, and then booted it up from there. So starting from an existing image and then add any additional software that you need. You can also create your image from scratch, and for this you would get the installation media. Those, if you're in my generation or older, you maybe had floppy disks or CD-ROMs or maybe even DVD-ROMs that had all of the software on it. So you could get that installation media. Now you can just usually download it or get it maybe on a USB thumb drive. And once you've got that, then you can boot your new machine from the install media, whatever format you have for that. And then that formats the machine's disk drive, copies the operating system onto the drive, and then adds the bootloader in its predetermined location. So basically, it's whatever had to happen for either of our first 2 options. You're just doing all those steps yourself rather than getting it from someone else. So the first 2 approaches, there are repositories of machine images, and they usually contain open source software. And those are available and provide a variety of minimal images with just the operating system kernels or other images that include complete applications, or everything in between. So those are really great starting points that can help you quickly try out a new package or a new program. But there are some issues that can come up when you pull down and run an image that you or your organization didn't create. So these are good things to be aware of, is that you can't control the version of the operating system in the software, depending on where you find the image. The image may have software that contains vulnerabilities, or it might not have been configured securely, or it could even have malware in it. It could have a virus or something. So those are risks that you take on, especially if you're not pulling your image from a reputable source. Also, things to keep in mind are that these virtual machine images can be really large, the very large file size. So transferring them over a network can be really slow. Sometimes download times take a while because it's a big image. The image is bundled with all of its dependencies, but you can build that virtual machine image on your development computer and then deploy it to the cloud, and you may want to add your own services to it, but it is good to keep in mind that sometimes those images can be very large. Now that we're done with images, let's talk about containers. Virtual machines solve the problem of sharing resources and maintaining isolation, but like we just said, virtual machine images can be really large, and transferring virtual machine images around the network can be very time consuming. Containers are a mechanism to maintain most of the advantages of virtualization, but they help reduce the image transfer time and startup time. If we go back to this picture we had earlier of the bare metal hypervisor, we can see that a virtual machine executes on virtualized hardware under the control of the hypervisor. In this image, we see several containers operating under the control of a container runtime engine, which is then running on top of a fixed operating system. And then that's running on top of the bare metal hypervisor. This sharing of the operating system represents a source of performance improvement when you're transferring images. The second source of performance improvement is the use of layers in these container images. So the containers here, that just makes it much easier to transfer those images. Let's combine the two ideas now, containers and virtual machines. What are the trade-offs between delivering your service in a virtual machine and delivering your service in a container? A virtual machine, it virtualizes the physical hardware, the CPU, the disk, the memory, the network. And the software you run on the virtual machine can include the entire operating system, and you can run almost any operating system. You can also run almost any program on a virtual machine, unless it needs to interact directly with the physical hardware. And even then, sometimes you can set up a way to pass that information through, that interaction through. But those physical interactions is important when you're working especially with legacy or purchased software. So that's something to keep in mind. Also, having the entire operating system allows you to run multiple services in the same virtual machine, and that's a desirable outcome when the services are really tightly coupled, they share dependencies, or when they share a large data set, or if you want to take advantage of the efficient inter-service communication and coordination that's available when services run within the context of the same virtual machine. And the hypervisor ensures that the operating system starts, monitors its execution, and restarts the operating system if it crashes. So that's also important to keep in mind. Container instances, they share an operating system, and the operating system must be compatible with a container runtime engine, which then limits the software that can run on a container. The container runtime engine starts, monitors, and restarts the service that's running the container, and the engine typically starts and monitors just one program in a container instance. If that one program completes and exits normally, then the execution of the container ends. One of the benefits of using containers is that the size of the container image is very small, and a drawback is that multiple services in a container could bloat the image size, and then that will increase the container's startup time and the runtime memory footprint. So there's some important things to keep in mind. One of the things that we like about containers are the portability. You maybe have heard of Docker. That one's a very, very popular container service. There's also Containerd and Mesos. There's different ways of managing containers. Docker is the one I've seen most often. There is something called the Open Container Initiative, and that initiative has standardized that interface between the container runtime engine and the container, and that allows a container created by one vendor's package like Docker to be executed in a container runtime engine provided by another vendor like Containerd or Mesos that I just mentioned. This means that you can develop a container on your development computer and deploy it to a production computer and have it execute there. Of course, the resources available will be different in each case, so deployment is not a trivial thing still, but it does simplify your steps. And if you specify all the resources as configuration parameters, so that you can have one set of configuration parameters for development and another set of configuration parameters for production, then that also makes the movement of your container into production even more simplified. So those are just important things to keep in mind for portability. It does simplify your steps, especially if you set up configuration parameters. But deployment is still, it's a big deal. Pods. What are pods? Kubernetes is probably the most common pod you've heard of. Kubernetes is an open source orchestration software for deploying, managing, and scaling the containers. And there's one more element in this hierarchy, and that's the pods. A pod is a group of related containers. So in Kubernetes, nodes, which are the hardware or the virtual machines, contain pods, and then the pods contain containers. That's what we have in the picture here. So you've got your node, which is your hardware, your virtual machine. Then you have your pods, and then you have containers inside of those pods. That's a way of grouping those containers. The containers in a pod then share an IP address and the port space to receive requests from other services, and they can also communicate with each other using inter-process communication, IPC, like semaphores or shared memory. So that's really useful for your containers to be able to share. They can share ephemeral storage volumes that exist for the lifetime of the pod, and the containers in the pod also have the same lifetime. They're allocated and deallocated together. So for example, service meshes, which we discuss in chapter 9, are often packaged as a pod. So the purpose of a pod is to reduce communication costs between closely related containers. We group them together because that gives them that more direct communication. If container 1 and container 2 in this picture communicate frequently, the fact that they're deployed as a pod and thus they're allocated on the same virtual machine, it allows for the use of faster communication mechanisms than just normal message passing. Okay? Serverless architecture. So remember, when we allocate a virtual machine, it starts by locating a physical machine with enough free capacity, and then it loads the virtual machine image into that physical machine. Physical computers, therefore, constitute a pool from which you can allocate resources. Now, suppose that instead of allocating virtual machines onto physical machines, you want to allocate containers into container runtime engines. That is, you have a pool of container runtime engines in which your containers are allocated. Load times for a container are short. They just take a few seconds for a cold start and a few milliseconds to reallocate. But virtual machine allocation and loading is relatively time consuming, and that can take minutes to load. And minutes doesn't necessarily seem like a large measurement of time, but when you're waiting for it to load and you're trying to deploy something so you can work or get it live, minutes versus seconds or even milliseconds is a really big time difference. So virtual machine allocation takes minutes to load and start the instance, and you typically end up having to leave the virtual machine running even if there's idle time because you don't want to sacrifice that time. In comparison, since the allocation of a container into a container runtime engine is fast, seconds to milliseconds even, it's not necessary to leave the container running. We can afford to reallocate a new container instance for every single request. This approach to system design is called serverless architecture. Even though it's not actually serverless, it just, I guess, has more of a feeling of less of a server because it's closer to instant than it would have been. Okay, so this is what we refer to when we're talking about serverless. And if you're familiar with Amazon's structure, AWS structure, we talked about Kubernetes already. Lambda is their serverless architecture service. That was a lot of information. Hopefully you kept up okay with what I was talking through for each of those topics from the chapter, but let's just kind of summarize and regroup on all of those different things. So virtualization has been a boon for software and system architects, which provides efficient, cost-effective allocation platforms for networked services like web-based services. Hardware virtualization allows for the creating of several virtual machines that share the same physical machine. It does this while enforcing the CPU, memory, disk storage, and network isolation. And consequently, the physical machine's resources can be shared among several virtual machines, while the number of physical machines in an organization must purchase or rent is minimized, which is even nicer when you're working in the cloud, which again, we'll talk about the cloud in chapter 17, but being able to spin up a test just for a proof of concept without having to purchase more physical hardware is a huge deal, especially for small startups or for companies that want to experiment or try out new technologies. A virtual machine image is the set of bits that are loaded into a virtual machine, and that enables its execution. There are various techniques that we can use to provision, that we can use to create virtual machine images, like using operating system functions or loading a pre-created image, so that we can provision virtual machines using those images, and we can get those images in several different ways. Containers are a packaging mechanism that virtualizes the operating system, and a container can be moved from one environment to another if compatible container runtime engines are available. The interface to container runtime engines has been standardized by that open container interface system that I talked about. You can also place several containers into a pod, and that means that they are allocated together, and any communication between those containers can be done quickly. Finally, serverless architecture allows for containers to be rapidly instantiated and moves the responsibility for allocation and deallocation to the cloud provider infrastructure, like Lambda. All right, I hope you got some new things from chapter 16, and we will see you in the next chapter. Thanks, everyone.